Hello, we are the Husky Robotics team here at the University of Washington. Now in our 9th year, COVID-19 has disrupted our usual design and manufacturing schedule. We recently transitioned to in-person work after almost 1.5 years of hybrid or online meetings. Nevertheless, we have created novel iterations, developed our most capable soil analysis system, and produced effective software for our most reliable and advanced rover yet, Resurgence.
Our new arm is stronger, streamlined, and more functional than ever. Our most notable change has been replacing our forearm with a brand new aluminum strut that allows the electronics to be internally mounted, providing more protection while also being lighter and cheaper. Our new worm-driven shoulder is compact yet powerful, allowing the elbow, which has been reduced in complexity, to move the arm to any position. Our new hex axles are also much more serviceable than keyed round shafts, and our novel quick swap hand mount uses a pogo board to allow us to swap out hands mid-competition without the use of any tools. We have designed a variety of end effectors that will more effectively complete the tasks without having the weight of extra features in a single hand. In addition, our extensive use of FEA has allowed us to maintain the weight of the arm while also improving its strength.
Due to manufacturing constraints from COVID-19 restrictions, we had to focus on improving last year's mobility unit this year. This unit includes a passive linked rocker system that conforms to uneven surfaces while remaining stable, a quick release system to swap arm and instrumentation out, and drivetrains that are sealed and mechanically isolated inside the hollow dual bearing spindles. It is capable of driving at a max speed of 1.1 meters per second and up inclines of up to 40 degrees. SolidWorks and MATLAB simulations were used to validate the critical components against static and dynamic loads that we expected during the extreme retrieval and delivery mission. Modifications for URC 2022 included a new rocker bearing for added rigidity for arm, and improved gearboxes for faster traversal speed.
Our science station has been upgraded to allow collection of up to 6 soil samples with a new auger-equipped arm that allows for more effective subsurface soil collection. Individual sample cups are sealed with a rotor as the samples rotate between tests to prevent contamination and spills. To aid in our search for life, we are employing a microscope and 2 protein assays to collect geological and biological information. A humidity probe will look for subsurface moisture, and a magnetic agitator will ensure that our assays reach as much of the sample as possible. Our rover will monitor UV intensity, carbon dioxide concentrations, volatile organic compounds, temperature, pressure, and humidity.
The electronics subsystem has been dedicated to creating reliable, modular, and functional systems for the upcoming rover's motors and servos. To reduce miswiring and the amount of wiring used for network communications, we have replaced wire connectors with stacking headers. These help to reduce the overall footprint of the electronic components inside the rover chassis. For additional field contingency options, all of our current electronics are compatible with previous designs, so this allows us to replace any components when we need to in the field and have spare backup ports.
Our rover is controlled through custom embedded circuit boards that manage power distribution, motor controls, and telemetry data collection. They communicate with an NVIDIA Jetson controller over a CAN bus. Each board has integrated voltage and current protection and is controlled using team-built firmware. Our custom CAN protocol emphasizes sending status data and telemetry to the Jetson and base station so we can monitor resurgence and maintain a given position or speed so the Jetson can keep focused on high-level control, video processing, and autonomous operation. This system helps facilitate inverse kinematics for controlling the arm.
In the past year, software has improved on our autonomous navigation by implementing differential GNSS, fitting GPS RTK receivers to our rover and base station antennas for greater positional accuracy and drift correction. We've made a 3D rover simulator in the Unity game engine, modeling physics, rover and arm motion, and sensors. Our simulated sensor data includes GPS coordinates, accelerometer, gyroscope, and heading information, LiDAR, obstacle detection, and cameras, with simulated noise for each to model the actual hardware. We have also implemented a depth visualizer, using a stereo camera to give arm operators more information for the equipment servicing mission. Our computer vision systems use an OpenCV pipeline to localize AR markers relative to the robot, using adaptive thresholding to compensate for differences in lighting and a global shutter camera to avoid artifacts caused by motion. Finally, we've updated our web-based mission control interface to better incorporate camera feeds and group relevant controls for URC missions together.
We'd like to thank the following sponsors: